For problem 8, we're given a polynomial f of x, and we're asked to find intervals where the function's increasing, where it's decreasing, concavity, extreme points, and inflection points. And I've grouped increasing, decreasing, and extreme points together because they all rely on the first derivative. So our first step is to compute the first derivative. So if I look at my formula and I look at each term, 63, its derivative is 0. The linear term negative 51x has a derivative of 51. The term 13x squared has a derivative of 26x, and the x cubed term has a derivative of minus 3x squared. Now we usually like writing that in decreasing powers, so we get negative 3x squared plus 26x minus 51. And we really want to do some sign analysis on this, and a graph would certainly help. So if I graph this polynomial on my graphing calculator, I would see that the graph looks something like the picture I've shown, and it really looks like this first root is at x equals 3. And the way that I verify that is I use synthetic division. So I write my coefficients, negative 3, 26, negative 51, and I would like to test to see if that has a root at 3. So I just go through the steps of synthetic division, and sure enough, I discover that my first derivative factors. Now that I've factored my derivative, I can do sign analysis. So I'll look at the factors, and each factor will give me one of the roots. So I know that I have a root at 3 for my f prime function, and I really should label this sign analysis line. And if I look for the second factor, I get a root from this second factor of x equals 17/3. And so there's a second root at 17/3. And from our graph we can see that the signs are negative, positive, and negative. And now we're ready to interpret. Our derivative is greater than 0 on an interval that goes from 3 to 17/3. And that implies, we draw our implication arrow, that implies that the original function is increasing on the same interval. Similarly, my derivative is negative on a union of two intervals, negative infinity to 3 union 17/3 to infinity. And this allows me to imply that f is decreasing on each of those intervals, but not the union. So I say it's decreasing on minus infinity to 3 and on, let's put that on a new line, (17/3) to infinity. So now I've got that my original cubic is decreasing on the interval negative infinity to 3, it's increasing on 3 to 17/3, and then it decreases again on the interval 17/3 to infinity. And this allows me to conclude things about the extreme points. We have extreme points extreme values at x equals 3, which is a local minimum, and at x equals 17/3, which is a local maximum. Continuing this problem, we now want to look at where the functions concave up and concave down and inflection points, and these are all based on the second derivative. We've already found the first derivative, so our next step is to compute the second derivative. Once I have my second derivative, I want to interpret, or I want to analyze doing sign analysis. So analyze for the signs. And to do that, I need to solve f double prime of x equals 0. I'm looking for supercritical points. So negative 6x plus 26 equals 0 gives me x equals 26 over 6, which is 13 over 3. Once I find the roots, I can create a sign analysis number line. I put my root 13/3, and again that's a root for the f double prime function. And I can now plug in values. F double prime for 0 is positive, and f double prime for something big, say 6, gives me negative. And so I can interpret the sign analysis. And interpreting the sign analysis is the key step. We look at our sign analysis, and wherever the second derivative is positive, it allows us to determine where f double prime is greater than 0, which is on the interval negative infinity to 13/3. We know that this tells us, so we know that this implies that our first derivative is increasing, which is what it means to say that f of x is concave up. So we say f of x is concave up on negative infinity to 13/3. At the same time, our sign analysis also lets us identify where f double prime is less than 0. And in this problem, it's on the interval 13/3 to positive infinity. And so this is enough to imply for us that f of x is concave down on that same interval, 13/3 to infinity. Because our concavity switches at 13/3, x equals 13/3, x equals 13/3 is an inflection point because the concavity switches at that point. And that completes our problem. Problem 9 is similar to problem 8. We were given a polynomial. We want to know where it's increasing, decreasing, concave up, concave down. We want to find all the extreme values, and we want to find all of the inflection points. So our first step is to compute the first derivative. And so when we compute our derivative, it's useful for factoring purposes maybe to recognize that we could factor out a -2. So I get -2 times 2x cubed plus 9x squared plus 8x minus 3. And this allows me to focus in on my possible integer roots. They're only plus or minus 1 and plus or minus 3. And at this point, if I had a graphing calculator, I'd graph this and see which of those integers are actual roots. Based on the graph, I see that there appears to be a root at x equals -3. I can verify this using synthetic division. So I set up my synthetic division table, and I go through the process. When I do this, I discover that the remainder is in fact 0. And notice that I used the coefficients of my deflated polynomial. I've already factored out the -2. There's no point in doing that again. So I can now rewrite my f prime function. F prime is -2. Keep that same factor I started with. X minus -3 is x plus 3. And then this quadratic that I'm left with, 2x squared plus 3x minus 1 is my second factor. And now, if I want to find additional roots, I'll look at the quadratic formula. So I use the quadratic formula for any additional roots. And so let's see how I would do that. I would say my 2x squared plus 3x minus 1 function equals 0 has solutions x equals -b plus or minus square root b squared is 9 minus 4ac. -4 times -1 is +4 times 2, so we get plus 8 all over 2a, so 2a is 4. And so my other two roots are these interesting points, -3 plus or minus the square root of 17 divided by 4. So they don't look like simple numbers, but yet they're still my roots. And so I can now do sign analysis. So I create a number line, and I indicate each of my 3 roots. I happen to know the order because of my original picture. When I looked at the graph of f prime, I saw that -3 was furthest to the left, and so I have my 2 other roots. Again, based on the picture, I already know the signs. I'm going to have a negative, then positive, then negative, and then positive because of where the graph is on relative to the axis. So my derivative signs are now known, and so the last step is to interpret this. Based on my sign analysis, my first derivative has a positive sign on intervals -3 to this funny root, -3 minus root 17 over 4, and also the interval -3 plus root 17 over 4 to infinity. While it's negative on the interval -infinity to -3 as well, so we do a union, as well on the interval joining my 2 quadratic formula roots. And so I can interpret this where the first derivative is positive allows me to conclude that my original function is increasing on each of the separate intervals. So I'll be increasing on the interval -3 to -3 minus root 17 over 4. And on the interval that's -3 plus root 17 over 4 to infinity. And where the first derivative is negative allows me to conclude that the function is decreasing. So I'll be decreasing on the interval minus infinity to -3, and on the interval joining those 2 quadratic roots. So -3 minus root 17 over 4 to -3 plus root 17 over 4. Because I switch at 3 points, I get 3 extreme values. I have 2 minima, so f has minimum at x equals negative 3, where I go from decreasing to increasing. And again, at x equals negative 3 plus root 17 all over 4. These are both local. They're not necessarily global. F has a local maximum at the other critical point at x equals negative 3 minus root 17 all over 4. To continue this problem and to deal with the concavity and inflection points, we'll need to compute our second derivative. So I calculate the second derivative using our rules of differentiation. And this time, I again want to factor out common factors, and I have a common factor of negative 4. So I get negative 4 times 3x squared plus 9x plus 4. And that doesn't look like it factors very well, so I want to find the roots, and to find the roots I'll use the quadratic formula. So the roots, I use the quadratic formula, solve 3x squared plus 9x plus 4 equals 0. There's my equation, and the solutions are x equals negative 9 plus or minus square root b squared is 81 minus 4 times 12, so that's minus 48, all over 2a, so that's 6. So when I simplify that, my supercritical points, negative 9 plus or minus, see, 81 minus 48 is 33. And so I now can do a sign analysis of f double prime. So I created a number line. I marked down my two supercritical points. Those are roots. And then I noticed that my second derivative is quadratic with a negative leading coefficient, so its signs will be minus, plus, minus. And I now interpret those to figure out concavity. So my second derivative is positive on the center interval. So I would write it's greater than 0 on the interval from negative 9 minus root 33 over 6 to negative 9 plus root 33 over 6. So that's the interval on which it's positive. Meanwhile, the second derivative is negative on two intervals, which we write a union, negative infinity to negative 9 minus root 33 over 6, union negative 9 plus root 33 over 6 to positive infinity. And we interpret this, they allow us to conclude that my function f is concave up on the center interval, so negative 9 minus root 33 over 6 to negative 9 plus root 33 over 6, and f is concave down on two intervals, on the interval minus infinity to negative 9 minus root 33 over 6, and on this interval negative 9 plus root 33 over 6 to infinity. Finally, we get our inflection points by looking at where concavity changes, and so my function has two inflection points. F has inflection points at both of these supercritical points, negative 9 plus or minus the square root 33 over 6. And that finishes the problem.